working. Excuse me. Just give it a few seconds to make sure things are working. So hello and welcome. Another couple more hours of LeetCode live stream. Do some LeetCode problems, see how it goes. Oh, this is taking a while, huh? Okay, it's working. LeetCode live stream. Hello, hello, hello. Do some LeetCode problems, see how it goes. I think so. Oh, this is taking a while, huh? Okay, it's working. Nice. All right, cool. Yeah, it's like a full minute of trying to make sure that the thing is working here. All right, great. So, I think I just got right into it, man. These are LeetCode easies. Let's go all the way down here. Or I gotta go so far down. I gotta go so far. Maybe I could filter problems I haven't solved. Oh wait, did we already find one? We already found one. Okay. All right, merge strings alternately. Okay, let's see this one. Hopefully my computer isn't too slow. I think I might need to restart my computer at some point here. It kind of gets, something weird happens with the computer after a while. It just goes really slowly. It's kind of annoying. Okay, it's having some issues. Okay, no, that's fine. All right. You are given two strings, word 1 and word 2. Merge the strings by adding letters in alternating order, starting with word 1. If a string is longer than the other, append the additional letters onto the end of the merge string. Okay, so this is pretty straightforward. This is kind of a nifty thing you could do with this. Let's do it this way. So we're going to make these references. And we're going to return the result. And we're going to do for I 0, j 0. I is less than word 1. And are they the same? Oh, okay. We'll do n. What does it say? It says additional letters onto the end. Okay. One dot size, two dot size. And we're going to say I is less than n. We're going to have a toggle. Which one it starts with, I think. Starting with word 1, okay. So we'll say j plus equals toggle plus equals not toggle. And something like this, I think, works. And then toggle. It's not. Okay. And we could do, like, it could be first word. First word. Make it true. So I will be plus equals first word. And then j is not first word. And then first word can toggle. And then you would say result plus c. So if for first word. Can actually do Yeah, it's easier to do it this way. There may be a better way to do this. We'll do it like this. First word, result plus equals word 1 of I. And otherwise, this equals word 2 of j. And then at the end, we're going to say word 1 dot size, word 2 dot size. It's greater than word 2. Then we're going to say result plus equals, I guess it's going to be like word 1, like, I kind of want to like get part of word 1, and then otherwise, I'm going to do word 2. You could do it like this. Maybe we'll do I and j plus n, I think. This is probably okay. It kind of copies the rest of the word, which is maybe not the best, but it's also not terrible. Something like this works fine. How about this one? So how's the stream health? Good live stream. Hello, 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 hello. Seems to be working. Oh, uh-oh. Something happened. Okay. What did we do? Wrong. Okay. Oh, gee. Well, that's not good. It's A, P, B, Q, and then RS. Okay. Interesting. Huh. Almost, I guess. I'm not sure if maybe this is the way I should do it. No. Yeah, I missed the last letter if I do it that way. Oh, not maximum, minimum. That's my mistake. Okay. I was like, didn't I do this right? That's probably the mistake. Yeah, it's gonna be hard to debug if you miss that part. There we go. Okay, I think this is correct. I'm gonna go for it and see how it goes. It may not be the fastest way to do this, but I think it's correct. There we go. Pretty good. Except it's on the slower side. There's probably a better way to do this. For sure, you could use pointers here instead of, oh wait, no, it still gives you 0. Yeah, that's fine. It's fine. So a couple optimizations would be to use pointers here instead of indices. And then the pointers themselves can be reused down here. I want to say there's like another way to do this append that's like a little bit better. This is okay, but I think there's a way to do this that like optimizes a little bit further. But anyway, we'll leave that for now. Okay, let's actually ask the AI about it. I think it's a good idea to do this every now and then. Let's try doing. Huh. So the stream is still buffering, I think. Gonna refresh. Critical logical error, it says. Okay. Oh, it's flawed. Let me see. No. Critical logical error. Okay. Iterates while both indices are less than n. The condition which causes the loop to continue correctly. In the case where one string exhausts those characters within the first position, the loop basic characters are accessed. Depends the many characters. Standard efficient approach. Substring I. Alternate characters of both strings of characters. Concise version, strings exhausted. Okay. The maximum of these two. I like this one. I like the latter code. Just see what the, yeah. Okay. Just kind of curious about this. I think there's, but yeah, I like the approach they gave. Actually, that's a lot better. That's a much better approach, much cleaner. Yeah, this is much better. Much cleaner, much simpler. I like that a lot. Append, okay. Reserved memory. Append. Okay, cool. Just kind of curious about these things. Gonna submit this one, see what works. Oh, internal error. I was like, what? What? Reserve, I think. Oops. Hmm. And here's another slight optimization. You ready for this? Let me see if this is still correct. Okay, you ready? Um, oh no. Well, this will always append to it won't work. Never mind. Never mind. Let's do M and N. I did this wrong. Okay, ready? Oops. Let's go back to not it's the minimum, right? Now, if I is less than the word size, so dot append. And do the same thing on the other side. Okay, how about this one? How about this one? That's a lot cleaner. I like that one better. That one's a lot better. Yeah, it's much better. most efficient implementation of this problem. Eliminates branching in the hot loop. Previous concise version checked on every iteration. Calculates limit once loop. Runs 0 conditional checks aside, allowing the CPU to optimize the pipeline perfectly, maximizes memory efficiency, retains the reserve call to prevent allocations, reallocations, uses append with iterators, the remainder, avoiding temporary string objects, input logic, only the common case for both strings of characters. Post loop, handle the edge case, remaining characters cleanly, so that using 2 if statements instead of if else is safe, because I can only be less than the size of one of the strings or neither, never both, after the loop finishes. Yeah. And remainder efficiently. Combines the logical clarity of your first solution with the performance benefits of reserve and append, while removing the runtime overhead of the Boolean toggle loop condition checks. It's the ideal balance of readability and speed. There we go. Beautiful. See, this is how I should be writing the code. Clean, clear, efficient, etc. I don't always write code like that, but ideally that's how I do it. All right, go to the next one. Excuse me, minimum operations to make the array increasing. You were given an integer array nums, 0 index in 1 operation. Let me just check and see. Yeah, okay, got some time. One more check here. That's good. That's good. Can choose an element of the array and increment it by 1. For example, nums 1, 2, 3 can choose to increment nums 1 to make nums 1, 3, 3. Return the minimum number of operations required to make nums strictly increasing. Okay. Strictly increasing if nums by is less than nums by plus 1. Array of length 1 is strictly increasing. So the simplest thing to do is just move left to right and say, okay, for basically each pair, right? For each element and the element next to it, A and B, if A is not less than B, which it is in this case, but it's not in this case, you add the elements to B to make it larger than, so you take the difference and add 1. So you'd add 4 from A minus B plus 1, you'd add that amount. And then on your next iteration, make sure you add that previous amount to your consideration. So this would be 6 now. And now again, you do A minus B plus 1 is 3. This becomes 7. And then the next consideration is going to be 7 to 1. You'd add 8, which would be another 7 that you add. So here you would add 4. Then you would add another, I guess you would update the number. You can actually just write in the number. It's easier if you just write it in. So this becomes 1, 5, 6. Add 3 to 7, so 4 plus 3 is 7, plus another 7 is 14. Yeah, that's probably the easiest thing to do. You don't have to write in the values, but it's a little bit easier to handle this logically if you do. So we'll do that. This isn't too bad. You just have this here. Constant A is nums of I, B is nums of I plus 1. Say result plus equals. Let me just say constant diff. It's going to be, assuming A is larger than B. Yeah. Just make sure it's non-zero. A minus B, and then we're going to update nums of I plus 1 is equal to I plus equals diff. And that's it, I think. Yeah. You could just put this here. I think that's it. Something like this we could see. We could see if this works or not. Yeah, I think that's it. I'm gonna go for it. It could be wrong, but I think it's right. Yeah, pretty straightforward. Not the most efficient though, interestingly. Let me try again. I think because I'm doing some, they're not the most efficient. Could be better. Let's do this here. All right, let's do we can instead do like a previous value. This might be more of what we're looking for. Maybe, I don't know. I think a little bit harder about this. Is that correct? I didn't prove it or anything. I didn't really think too hard about whether this is correct or not. Oh, it looks like it's correct. Okay. Okay, that's a bit better. Yeah, this could start off at 1. And then just say hi. And that's probably easier overall. Interesting. Okay. Correct and optimal, greedy approach, calculate difference, and single pass, few integer variables. Minor optimization, simplify the variable use, retract the previous value. Yeah. Let's see. So yeah, it's pretty good. No side effects. Previous variable, extract the adjusted value of the previous element, avoid modifying the input nose vector, preferred, put mutabilities required or expected. Loop starts from I equals 1, naturally comparing the current element against num's I against the adjusted previous value. This eliminates the need for I plus 1 checks and makes the iteration bounds clear. Time complexity remains ON. That should be optimal efficiency previous solution. After unnecessary increments, tracks the value. How much nums of I must increase be strictly greater than previous updated to b plus diff, the new value of the current element to the next iteration, arguably the most robust and production ready implementation. Okay. Right. So this is arguably the most robust production ready. already optimal, micro optimizations, constant factors, and improve runtime performance on LeetCode, tests a single process, disable synchronization. Okay. So start of your function or static initializer. Okay. Oops. Should this sync fast IO? I think I usually see it outside of the solution class. Standard and fastest. Guarantees it runs at once. Outside also runs before main, but managing state across LeetCode's internal test harness. Sometimes be unpredictable if not handled carefully. Leaking state between unrelated problems if the environment is perfectly reset, though rare. Okay. No performance penalty. Okay. Okay. So how about the static lambda? Okay, constant reference of raw loop values in loop. This is good. Make it even slightly faster. You can use a range-based for loop starting from the second element, though your index-based approach is already very efficient. How would I create range-based? The second. I actually don't know how to do that. I'm sure there's some way to do it, but I don't know what they're referring to exactly. Avoid std max override optional. It's usually in line replacing with a simple ternary operator if statement. Sometimes shave off nanoseconds in tight loops. Modern compilers handle std max very well. Speedrun version. Operations. Current. Diff operations. Current plus diff. Current. Effectively previous plus one. Yeah. So you either add one to the previous or you leave it as so you can update previous to be the number. I think I can obviate the if statements. Most fast IO block. Okay. Cannot directly specify a start index in the standard range-based for syntax. Okay, that's what I thought. Can achieve this cleanly using iterators in the range expression. This combines the readability of a range-based for loop with the flexibility of starting a specific position as the start and the end. Range-based loops accept any pair of iterators. Oh, it is range-based. Okay, I thought it was the. That's the iterator syntax. I don't know. I guess you call it range-based. Standard iterator loop. Okay. Range-based syntax specifically does not. Yeah, I was gonna say it does not support offsetting the start directly in the range part. Let's use views. Must use a standard helper. Okay. Iterators explicitly. True range based. C++ 20. You can use views drop 1. Okay. Different previous and current. So I have to clear in just as fast. Okay. Got it. I think I can eliminate the if statements, or rather the syntax. So what I could probably do, let me try this. So I don't have if statements. I have the max, step max, which is kind of like an if statement, but I can actually eliminate that, I think. Okay, it's fast, but it's not as fast as it could be. So what I might do is auto pointer speaking +1 nums.end. Dereference the pointer. So, I mean, this is one way of doing it too, but not quite getting rid of the if statement altogether. Integer arithmetic properties. Yeah, this is what I was thinking. Not well, not exactly. I'll show what I was thinking. Still on the slower side for some reason. So I think I can do. So previous is going to be equal to, it's either plus equals 1, or so we'll do constable check is going to be pointer is greater than or previous is greater than pointer. So we can add the check or not check times pointer or times b. Right. So if b is larger than previous, then this check fails, and previous ends up just being b. Or excuse me, it ends up being, it should be equal to if the check doesn't fail though, then we should increment the previous by 1. So it's either going to be equal to, when check is 0, we get previous, no. Okay, these are the two values. And when check is 0, this gets canceled and we get b. When check is 1, this is what we end up with, and this disappears. So that handles the two different branches as multiplications instead of if statements. The difference as well is going to be between previous and b. You could do diff is going to be could do greater than 0. It's previous minus b plus 1. Yeah. And the same thing here, result plus equals check times diff. So if the difference is positive, how we add it. How about this one? I think that's correct. Slightly more sophisticated approach. There we go, that's 100%. Beautiful, 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 beautiful. All right, the AI probably doesn't know how to do this. Can eliminate this integer arithmetic properties. Diff is only needed when previous greater than current. The formula previous minus current plus 1 yields a value less than 0. It's equal to 0 when no operation is needed. Adding a non-positive diff to result changes nothing. And adding it to current to update previous effectively just sets previous to current plus previous minus current plus 1 equals previous plus 1, which is incorrect for the case where the array is already increased. Wait, that's really valid. The current's greater than previous, when diff is 0. Formula gives a negative number. If we add the result, subtract operations, wrong. If we update, current was 10, we incorrectly lowered previous. Cannot simply remove the check. If you're accumulating result, then updating previous in one go, because negative values will corrupt the total count in the sequence. Can eliminate the if branch by using the trick. Only add to result if the difference is positive, but that brings us back to a conditional. Is there a branch this way? Yes. Using the fact can be computed with a bit manipulation arithmetic, but in C++. SIDMAX is usually compiled to a conditional move construction, which is already branchless on modern CPUs. Likely cannot safely eliminate the logic that handles the no operation needed case without breaking the math, unless you restructure the loop to only process pairs that violate the condition, which requires an if or a complex index jump. The SIDMAX approach you have is already the most concise, correct mathematical representation representing it. Replacing it with manual bit hacks or arithmetic tricks to avoid SIDMAX usually makes the code less readable without getting performance as the optimizer compiler optimizes SIDMAX perfectly. Did you have a specific arithmetic and trick in mind? I might be missing a few clever insights. Oh, so it does know how to do this. Okay, never mind. Absolutely with me. You have successfully implemented a branchless solution by replacing the conditional logic with arithmetic. Bool implicitly converts to an int. Your code leverages this. Leads to 1 if an operator is needed. 0 otherwise. Check is 1, previous becomes previous plus 1. Check is 0, previous becomes b, so it's not check is 1. Result. If check is 1, adds diff to the result. Check is 0, adds 0. Faster, theoretically, yes. Eliminates the potential for branch misprediction penalties. The CPU executes a straight line arithmetic instructions without jumping. Practicality. Practically, modern compilers are extremely smart. Your previous STDMAX or if version often compiles to conditional move instruction, which is also branchless. Your new version forces multiplication and addition. CMove uses a single CMove instruction. On modern x86 where CPU CMove is often slightly faster or equal to multiply add sequence because multiplication has higher latency than a move. Code is correct and genuinely branchless, while it might not be measurably faster than the STDMAX version. Modern hardware due to CMove is a fantastic example of branchless programming techniques often using GPU shaders or highly constrained embedded system where conditional moves are expensive or unavailable. Okay. So the CMove actually as fast as this approach. Is that correct? Doesn't run into branch prediction issues. So I'm not sure about this actually, how this works. But this gave me a faster runtime. Excuse me. CMove does not suffer from branch prediction penalties, but your assumption that it is always as fast as your Boolean arithmetic approach needs nuance. CMove caused branch prediction issues. No, CMove is not a branch. Branches change the instruction pointer. The CPU must guess the target to keep the pipeline full. A wrong guess flushes the pipeline. CMove executes sequentially. The CPU already knows exactly what instruction comes next. It simply waits for the condition flags to be ready and then moves, or it doesn't move. The data is zero misprediction penalty. As fast as your Boolean arithmetic, not necessarily. In fact, your Boolean arithmetic version might be slower than CMove on modern CPUs, and CMove itself has trade-offs. Cost of your Boolean arithmetic. Multiplications, additions, and negations. Latency, integer multiplication fast. It's higher latency, typically 3 cycles. Throughput costs compared to a simple move. Dependency chain, you force the CPU to calculate both paths and blend them mathematically. Compiler generates CMove, ifs. Operations, compare CMove. CMove is essentially a move that depends on flags. It is very fast with cycle throughput and moderate latency. Creates a data dependency on the flags, but avoids the heavy multiplication instructions. Trick cases. Dependency chains, critical trait. They both compute both values. Your loop for the next iteration depends on the CMove multiplication finishing. This creates a serial dependency change. CPU cannot start the next iteration's comparison until previous is fully calculated. Branches, if perfectly predicted, can sometimes break this chain earlier via speculative execution. CMove is likely faster because it avoids expensive multiplications. Your trick replaces a branch with heavy math, which is often slower than a simple conditional move. The data is random. CMove wins. No risk prediction. Data is nearly sorted. Branch predictable. Branch might win. Due to speculative execution, breaking dependency chains. Stick with std max of the if statement. The compiler will emit CMove automatically when it detects unpredictable patterns, giving you the best of both worlds with the overhead. Okay, so the manual application is actually likely to be slower. Ah, interesting. Wasn't expecting that. Okay. So actually, we do. So we wouldn't need this check. We could do previous plus equals diff, b plus diff, and then or rather it's b plus diff, and then result plus equals diff. I think this is what I had, the code that I had before, something like this. Manual multiplication purchase likely slower at best equal. Huh. CMove has a latency of 1 cycle and throughput of half to 1 cycle on modern x86 64 CPUs until Skylake Plus. AMD Zen Plus is essentially a free move. The flags are ready. Integer multiply has a latency of 3 cycles and throughput of 1 cycle on most modern CPUs. Even though it's fast, it's strictly heavier than a move operation. Instruction count compiles to 2 instructions. Compiles to compare, set G, multiply, add 6 plus instructions, forcing the CPU to execute more operations to achieve the same result. Branchless misconception. The goal of branchless code is to avoid misprediction penalties. CMove achieves this perfectly without branching. Placing CMove with multiplication removes the branch but adds arithmetic latency. Since CMove already has no branch penalty, you're trading a free instruction for an expensive one without getting it. When would your approach be faster? On very old CPUs where CMove was notoriously slow and multiplication was relatively faster. On any CPU from the last 15 years, CMove wins. Final breaks at the std max of the ternary operator. Compiler will generate the optimal CMove instruction, giving you the best possible performance of the cleanest code. Manual optimization will clever introduce unnecessary. Ooh. So, stand corrected. It does know how to do. It does know how to do what I'm describing. It's just, it's not the best approach. Okay. There you go, 100%. Okay. Good to know. This is why we practice, right? This is why we practice. Find triangular sum of an array. You're given a 0-index integer array nums, where nums of I is digit between 0 and 9 inclusive. The triangular sum of nums is the value of the only element present in nums after the following process terminates. The nums comprise of n elements. If n equals 1, end the process. Otherwise, create a new 0-index integer array. New nums of length minus 1 for each index I. Assign the value of new nums as nums of I plus 1 mod 10, where mod denotes modular operator. Place the array nums with new nums, repeat the entire process. Step 1, turn the triangular sum of nums. Okay. So we've actually already seen a similar question. So we're going to add these two. Oh, wait. Oh, yeah, okay. So we add these two, and we add these two, and these two, and so on. But this gets added once. Then this gets added once. This will get added twice. And then when you add here and here, you're going to have 1 plus 2 plus 2 plus 3, right? Basically, this is each number appears once. Then each number is going to appear once, twice. This will actually appear twice, and this thing twice, right? So once, twice, 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 once. Then these appear again, each of these, and you end up with thing 1, 3, 3, 1, something like that. Basically, these are like triangle numbers, like Pascal's triangle. It's very similar to Pascal's triangle. They're the number of times that the original elements appear. It's going to be a combinatorial factor in the sum at the bottom. So basically, you could add all of the elements together as you multiply them by a combinatorial factor. The combinatorial factor is going to be n choose I think. So you want to compute n choose I mod 10, and you're going to use I've already seen this question, by the way. You can use n choose I, and you can use, I think it's not Lagrange, not Laplace, but another factor. Let's see, ready for this question. Let me also see if the stream's okay. Yep, stream's okay. This is going to be calculating larger and choose R using modular operators. There's a very specific way to do this. It's called, no, not Fermat, Lucas. Not Laplace, not Legander, not someone else starting with Lucas. There's Laplace, there's Legander, and there's Lucas. And I tend to forget Lucas' theorem. This is the one you want. So you can say, basically you can break it into P is a prime number and then R non-negative integers of the base P expansions. You can rewrite n as a sum in base P, basically rewrite it in base P, which then is, and you can rewrite R in base P as well. And then you can take the n choose R is going to be the product of n sub I choose R sub I mod P, where and the proof of this is actually kind of interesting. It's not that hard. And you take the product over these values. Any digit R sub I is greater than n sub I, then this expansion is 0, make the entire product 0. Interesting. Would you kindly briefly outline proof? So we're going to use Lucas's theorem here with the Chinese remainder theorem, and both of those will allow us to do. We can calculate each of the binomial coefficients for mod 5, and then calculate for mod 2, and then just wondering if calculating for mod 2 is like any easier. Yeah, I think it's better to just use Lucas theorem twice for mod 2, mod 5 and mod 2. Typically relies on generating functions. Okay. Commutative proofs using group actions also exist. Okay. Algebraic proofs, the identity for a prime. Binomial theorem. Okay. Generalization powers. Excuse me. Decompose the generating function for any n based on its base p digits. Okay, coefficient comparison. Got it, combinatorial. N elements partitioned in groups of size p raised to the k dots p raised to the 0 corresponding to the digits of n by acting on the subsets of size r. The group of order p to the n one shows that only subsets formed by choosing exactly r sub I elements from each group of size n sub I p raised to the I remain fixed non-zero modulus p, leading to the same product. Okay. It might take a little while to really think this through, but basically Lucas theorem is the one we want. Lucas theorem with Chinese remainder theorem is the way to go. Is there a faster way? I would guess that there's a much faster way to do this. Bitwise operation. Simply the bits of n and r. Oh. Oh, I see. Possible values 0, 1, 1, 1. R to 0 if only existing index. N sub I is 0 and R sub I is 1. Corresponds exactly to the condition with the bitwise and if n and r is 3. Oh, okay. So that one's pretty easy. Okay. Cool. That's much easier. How about for mod 5? I think there's a similarly fast approach. All right, so we'll do it like this: const auto com mod 10, say constant n r 0 for now, and then we're going to say int result 0. Or int I 0, or it's really going to be x and nums plus equals, result is going to be result plus com mod 10 of n times r times x modulo 10. And this is going to be n and r. N is going to be, I think, nums.size. And r is going to be, oh no. I do need to use this index on. Times I. Or no, excuse me. Yeah, it's just I. Yeah. If it's 3 elements, first one gets added once. So if it's 3 elements, we get 1 added here and here, 2 added here and here. Yeah, so it ends up being 1, 2, 1, which is going to be 2, choose 0, 2, choose 1, 2. So I think it's n minus 1 for the for n, by the way. If n is 1, yeah, I think that's right. Okay. And for the combinatorial, we're going to say constant mod 2. It's going to be n and r equals r. Super clean. And then mod 5. Instantly is a mod 2 case. Simple binary logic key for capturing all conditions. Significantly faster approach than calculating factorials derived directly from Lucas theorem. Pairs of base 5 digits. If and only if any digit of r is greater than the corresponding digit is base 5. And r in base 5. Compare if r sub I is greater than sub I for any position. The result is immediately 0. Well, if no such position exists, the result is the product of the small pre-computed coefficients. Binomial p mod 5. It's fast, extremely fast. 25 possible values can be stored in a tiny hard-coded lookup table, making them a multiplication step. Lucas table, pre-computed table. Kummer's theorem. Returning only if the result is 0, divisibility. Kummer's theorem offers an equivalent check. At least one carry when adding r and n minus r in base 5. Logically identical to checking if any digit r sub I is greater than sub I. Okay, cool. So we can create the table. Static const stud array of stud arrays. 5 by 5 events. I don't remember where it goes exactly. I want to say it's something like this. Could write a function that calculates these values, but it's, I think, perfectly fine to write them directly because they're not too hard to compute. So we'll say n choose r. N choose r. 0, 5. Yeah. So 0 choose 0 is 1, 0 choose 1 is 1, 1, 1, 2, 3, 4, 5. 1 choose 0 is 1, 1 choose 1 is 1, 2, 3. Is that what they define it as? No, these zeros, okay. My mistake. Two choose 0, 2 choose 1, 2 choose 2, 3 choose 1, or 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, 3 choose 4, and then 4 choose 0, 4 choose 1, 4 choose 2, and this is all mod 5, by the way. Whoops. Yeah. Okay. Single braces. Brace elision allows you to emit the inner braces. So it's int number. Okay. Excuse me. And then we're gonna say NCR mod 5. I don't know if I need to capture this or not. Actually, I don't think I need to. So mod 5 is going to be 4. We're actually going to go ahead and make these if, say if n is less than r. So base 5 digits, you take mod 5 and then divide by 5 repeatedly. I think until they're both 0 is probably the way to do this. So for n is greater than 0 and r is greater than 0. or screw this here. We're just going to say constant d1 and mod 5, d2, so r mod 5. D1 is less than D2. We break terminate early. Otherwise, we're going to say mod 5 multiplies equals by and choose NCR mod 5. D1, D2. Yeah. Oh, and divide equals 5. Divide equals. Something like this. That gives me mod 5 and mod 2. Call this NCR mod 10. Okay, and then now we're going to CRT. And how would I use CRT? CRT to combine mod 5. I just forgot how to do this, quite frankly. Probably should remember how to do this, but I just don't remember it. Nested aggregate initialization, scalar initialization. Mid-theater braces. Partial initialization. Huh. Oh my gosh, look at this mess. You need the double braces. Oh. It's like double braces. Okay, interesting. Five, 8, 2, 6, 8, 5. Okay. Coefficients that isolate each modulus. Multiple of 5 that is equivalent mod to 1 mod 2. 5 is equivalent to 1 mod 2. The term is 5. Yeah, I think it's like if the sum is supposed to be, if you take the sum mod 2, you're supposed to get the mod 2 value back. And if you take the sum mod 5, you get the mod 5 value back. So it's something like a, let's say x plus by 2 value is mod 5 value. Then ax plus by mod 2 should be x and ax plus by mod 5 should be y. So what does that mean? Well, if we take this mod 2, the y value shouldn't matter what the y value is. The b value basically should be like a multiple of 2. And the a value should be a multiple of 5. So if you do like 5x plus 2y, for example, doesn't quite work. We take mod 5, we get 2 mod 5 times y. This should be times 2 inverse mod 5. 5 inverse mod 2 times x. 2 times 2 inverse mod 5 times y. Now if you did this approach, 5 times 5 inverse mod 2 times x, and now you said, okay, take both of these mod 2, this will disappear mod 2, or excuse me, this will disappear mod 5, and this will stay, and modulo 5, this will disappear and give you y. So this is y mod 5, and x mod 2. Yeah, and this ends up being, so 5 times 5 inverse mod 2. So 5 mod 2 is going to be 1, and inverse, that's just 1 mod 2. So x, that's just 1. And then 2 inverse mod 5. So 2 mod 5 is just 2. And the inverse should give us a 1. So we do 3 times 3 times y. 5x plus 6y. Which I think is what they gave us. Yeah. X I think was mod 2 and y was mod 5. Yeah. So 5x plus 6y mod 2 is going to give us x. 5x plus 6y mod 3 or mod 5 gives us y, right? Gives us this. So mod 2, this becomes a 1, but this becomes a 0. So we end up with x. And then mod 5, this becomes a 0, and this becomes a 1, which gives us y. So 5x plus 6y. Okay. 5 times x plus 6 times y, modulo 10. And this is going to be, what did we say? X was mod 2 and y is mod 5. Yeah. It's pretty good. It's pretty good. Last digit of massive binomial coefficients efficiently by combining the fast bitwise check and the base 5 digit check. Yep. Access elements. Ah. Say it ain't so. Oh. Yeah, initializing stuff requires a strong understanding of the syntax. It's correct. Extra set of braces for every row. Okay. Is it true? Huh. Yeah, so this is one of those things that grateful for some AI to help me out because oh my gosh, dude, the documentation is it's like really unnecessarily cumbersome to work through to figure something like this out. Interesting. But oh, maybe that's why. Oh, okay. I forgot to remove this. That will definitely cause your compiler some issues. Wrong answer. No kidding. Huh? I got 6, expected 8. Oof. I think this actually was correct, this first one. I think it was an issue somewhere further down the line that was causing problems. Let's see. So how is the stream health doing here? It's okay. No, it was a genuine compiler. No, it does need those braces for whatever reason. Okay. I suspect it's an off by 1 error here. I may have been correct the first time around that I needed one of these. No. Interesting. Maybe it's a -2. I don't know. I suspect this is the issue. Okay. Let's do a couple more test cases. Oops. Yeah, I think these are supposed to be digits. So I'm not supposed to have too many numbers there. Like, they're not supposed to be too large. Okay. Maybe the case that this could be optimized further, by the way. Something is wrong. Something is wrong here. All right. So maybe we do this one. Something's not right. Oh, I know it's. I don't know how I missed that. I don't know. There we go. I was gonna say, I thought I did think this through correctly. I'm gonna go for it. This could be wrong, but I'm gonna go for it. There we go. Got it. There you go. So that's how you do that one. Lucas theorem, Chinese remainder theorem, not too hard overall, not too bad. There are a few questions like this in the problem set. The CRT is a little bit odd, but yeah, it's basically values and their inverses multiplied across and added. I forgot how that works, but it's kind of peculiar. And then, excuse me, it's much simpler for only the 2' case. The 3', the case that has more primes involved is more complex. This is pretty interesting that you could just take the bitwise and you just have to ensure that they're both ones. That's kind of peculiar. Or they're both, yeah, they both have to match basically. Or they gave a truth table where they explained like what the deal is. So it's got to be, in order for there to be a 1, you have to have n is 1 and r is 1, or n is 0 and r is 0, so they're equal, or n is 1 and r is 0. So r has to be less than or equal to n, basically. Those are 3 cases where it's all 1. However, there's one case where it's not 1, which is when r is 1 and n is 0. And if you take the and in that case, you get a 0. Compare it to r, it's 0 compared to 1. That's a mismatch. That gives you 0. But if all of the cases n and r matches r, that basically means that r is always less than or equal to n. So if r is 0, it's always going to give you 0, and that's fine in that bit spot index. If r is 1, however, then it matters what n is, and n has to be a 1 in that case. If n is 0, you'll get a 0, and when you compare that to the r, it ends up being incorrect. I mean, that's not the easiest thing to figure out for sure, but that is interesting. That's how that works. Okay, so pretty cool. Not bad. I like this approach. Yeah, there's a few questions on the site that use this exact solution. This obviously scales pretty well for very large numbers. Large values of n. Okay. So yeah, how are we doing on time and the stream? We've got an hour now. Yeah, we've got another half an hour. Let me just check and see. Okay. We're still buffering. We could go to the next question, I think. Stream we've got an hour now. Yeah, we've got another half an hour. So stream health is it's not great for some reason. I don't really know why. Yeah, it buffered a lot today. Buffering. Okay, let's continue. So, next question is going to be, it's got another 30 minutes. Is object empty? Given an object or an array, return if it is empty. An empty object contains no key value pairs. An empty array contains no elements. May assume the object or array is the output of JSON operators. 2 key value pairs, so it is not empty. Okay, object is true. It doesn't have any key value pairs, so it's empty. 3 elements, it's not empty. Valid JSON object of array. Stringify, can you solve it in constant time? I have no idea. I have to look this. This is more of a syntax thing. JavaScript is empty array. Is empty. Is it a string? Output of JSON parse. Empty object. I'm not sure. What I'm supposed to do here. This is a syntax thing. I mean, I could look at the syntax on MDN, but ordered list with 0 elements, square brackets, length property. Okay, if is array and array length is empty. Okay, so it would be if array dot is array object and object dot length is 0. Okay. Okay. I gotta do three equals. And then what about empty object? An empty object is a collection of key value pairs with no properties. It is created using curly braces with the object constructor. Counting keys. Objects do not have a length property. Keys length, okay. If object and type of object is object. And the keys length, okay. Interesting, is that the object? BJ, type of BJ. Let's see the object. And object.keys of obj length is equal to 0. Actually, it's the other way around. This should be true. We want to know if it's empty. Not if it's not empty. I guess this is it. Yeah, this is more of a syntax thing. I just don't know the syntax for this. Let me submit this and see how it goes. Also want to know if I ask the AI about this, what does it think? Okay, so this is correct. It's pretty straightforward. It's not null. Object reference, the rule on properties already implies slightly streamline the logic. Perfectly readable and safe. So it's null is array. It's an object. Okay. Okay. No, I would guess it's not because the keys. No. Okay. Not for objects. Okay. Can use a for in loop with an immediate return. Okay. So this will be O1. Okay. So we can loop through for let key and object, for let key and object, and just have a quick return. Honestly, you could just do. Uh, Own properties. Okay. Um, isn't this a semantic thing? Okay. Industry standard Lodash turns true even if the prototype is polluted because it only checks on properties. Okay. Oh, interesting. So own properties. Okay, so that's yeah. JavaScript is crazy, dude. JavaScript. There's so many things about it that are just like, why? All right. Object prototype has own property. Object has own object key return false. Is empty. I think that's it. It's just object key. Wrong. False. True. So this would return empty. I mean, both of these return false, right? I think I need to do it this way. Something like this. Yeah. I'm gonna go for it, see how this goes. Okay, still ends up being the same speed anyway, but a little bit faster. Almost correct. Ooh. Okay, I do need to handle the null undefined case. Is it true or false? I don't know which one that's supposed to be. I'm not really sure. Reading the output. It's like, no, wait, no, wait, it does this, no, wait, it does that. Oh no. Oh, my god, that's funny. No, wait, hold on. I also appreciate how it uses the opening and closing parentheses. I like to do that. To like insert an extra comment. It's not really necessary to do that, but I do that anyway. You just add stylistic flair. Excuse I don't think I need to actually check that case. Hi, what's up, Roshan? Welcome, howdy. Hello, 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 hello. Hello, hello, hello. Okay, this works. Yeah, excuse me. Yeah, JavaScript's a little weird. JavaScript. All right, how are we doing on time? How's the stream health too? Okay, we got another 15 minutes. Man, stream health is not very healthy. Okay. It's very, what's the word for that? It's gonna buffer a lot. Let me refresh this. Let's see what happens here. Just give me 1 minute. Yeah, it's not a. It's been showing that it's been buffering for a while now. Hello, hello, hello. Yeah, it's not a. Okay. All right. We'll do maybe like a couple more problems, and then probably that'll be it for today. First, matching character from both ends. We're given a string s of length n consisting of lowercase English letters. Turn the smallest index I such that s of I equals s of n minus I minus 1. No such index exists. Return negative. Oh. Huh. Well, that's pretty easy. Okay. So this one's pretty straightforward. So yeah, if s of I equals s of I, what did we say was s I minus 1? Return I, whoops. And that's kind of it, man. I think. Yeah, that's a pretty straightforward one. There's not much more to say about it as far as like optimizing it. All right, we'll go to another one. Permutations already solved. That one's a little bit involved, I think. Not the simplest thing. Hello world, return a new function that always returns hello world. This seems kind of easy, man. I mean, is that... Some of these seem a little bit too easy. I am trying to do the easiest question, so I guess that's that. Kind of makes sense. All right. I don't know what to say about that one either. There's not much to say about those. Partition labels. Normally I would read out like what I did to solve these questions, but in the interest of time, I'm going to skip some of that. Given an integer array nums, in one move you may increase the value of any single element by 1. Turn the minimum total number of moves requires that all elements in nums become equal. Okay. So you just take the maximum value, multiply by the number of elements in the array. subtract the sum of the array. That's it. So this is very straightforward. So we're going to say constant max or max val. Just have to do a quick check on the values. It's only 100 by 100, and it's pretty straightforward. Okay. So this is going to be std max element nums.end, and we're going to say return max value times nums.size std accumulate nums. Let's try this here. Okay, stream is healthy. Stream is healthy. That's good. Great. Let me just listen here, see what it says. Stream is healthy. Oh, I got an error, huh? I didn't even notice that. I think I need a 0 there. I thought I had gotten it. Yeah. I think that's it. I'm not going to spend too much time trying to double check it. Pretty sure it's right. Yeah, that's good. Okay. Not bad. That's a pretty straightforward one. That one's not too hard to understand. Partition array such that maximum difference is k. Okay. Whew. All right. How am I doing on time again? I think we're at, yeah, we got a few more minutes. Okay. Integer array nums, integer k, may partition nums into one or more subsequences such that each element in nums appears in exactly one of the subsequences. Okay, so it's gotta be distinct. Okay. Minimum number of subsequence needed such that the difference between the maximum and minimum values in each subsequence is at most k. Subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. Minimum number of subsequences needed such that the difference between the maximum and minimum values in each subsequence is at most k. Oh, the subsequence itself. Okay. So we could use, and we could make a subsequence of everything. And what are the constraints here? 100,000 numbers, they can go up to 100,000. K could be 100,000. Okay, interesting. So yeah, if you make subsequences just one of everything, then that'll always, doesn't matter what the value of k is. K could be 0, and that'll work fine. Ooh, excuse me. Interesting. And each element appears in exactly one of the subsequences. So the minimum number of subsequences you're going to have is the frequency, the highest frequency. You have to have at least one subsequence per element that's larger. You could take the difference between the minimum and the maximum. So one approach to this would be consider the minimum and the maximum. Like if we were to sort this, right? If we basically you just use a sliding window left to right until all the elements that we're looking at have the maximum and the minimum. If those two values have a difference of k, then all of those can fit into, depending on what the frequency is of elements, all of those could be fit into subsequences. So you could use the minimum number of subsequences for that section. The issue, though, is these extraneous values, basically each of them need to get paired off with some other value that's k larger or k smaller, or they need to be paired off by themselves if no such value exists. You can actually do sort of a look ahead to figure out how far ahead you can go. Yeah, so you could sort the elements, take the first chunk left to right of elements. I think these subsequences need to be... Can't change the order of the elements, though, so that doesn't quite work. Okay. I guess the easiest way to go is just... Well, it's the minimum and the maximum, so we don't actually care. I don't actually know if we care about the order that much. No, the order doesn't matter. No, we can sort it. It doesn't matter. No, it's fine. We would just have to move our selections back to the original array, but it doesn't make a difference because the minimum and the maximum doesn't matter what the order of the sequence is. So yeah, subsequence doesn't matter what the order is. Okay, so we'll sort and we say, all right, we can only pick one of each unique element though. So you can move left to right from the first element and keep picking up elements until you reach the k maximum, but you can't pick up the you can't pick up duplicates. I think a greedy algorithm works fine. Yeah, because the duplicates, you have to fit them into another subsequence anyway. And you have to get the minimum element into something somewhere. So, and you stop at the first, because it's sorted, you just stop at the first element that's too large. You skip the elements that are duplicated. And you also put a little marker. That's where you're going to start next. And the ones that have already been processed, you skip them too. You could pop and swap them, I think. Yeah, the duplicates. Maybe a better idea to, could be a lot of duplicates. I'm wondering if it's better to use a frequency map of the 100,000 values. It might be better to use a frequency map. Yeah, it's probably better to use a frequency map. And then also I have to remember what that code was for the fast IO that I looked at before. I should probably hold on to that code. The static lambda call sets up the fast IO for LeetCode. I have it actually in this. I don't know if it's in this one. Let me see. No, it's not this one. What's the other one? Yeah, this is the code. So iOS sync with std.io false. cn.tie null pointer return null pointer. I don't know why this needs to return a null pointer, but apparently it does. Why does this code need to return pointer? I don't think it does. So it's sync with std. It's iOS syd. A lambda return type, so the goal is immediate execution. An IIFE immediate function expression. Okay. Requires the lambda return a value, so that fast can be initialized something. By null pointer, the code inside the lambda performs side effects. There's no meaningful data to return. Okay. Oh. Oh, okay. So it does need to. Okay, got it. Yeah, so it's oops. It's std iOS sync with std.io. Oops. Oh, go back. No. I didn't mean to do that. Std iOS sync with std.io cn.tie. False sync with std.io and cn.tie. Not entirely sure what this does, but this is interesting. Let me see if I can remember to put this here. We'll use it for this function. I'm kind of getting a little distracted here. So it's static const auto fast IO. Whoops. We actually call this function, and it's going to be std iOS sync with std.io false, and then std cn tie null pointer. I think that's what it is, right? Sync with std.io tie null pointer. Cool. Anyway, yeah, I'm tempted to use a a frequency map. The frequency map's a little bit easier to work with, I think. Shucks. The reason why I'm not so sure about it is that if you have heavily duplicates, you end up doing a lot of. If I just if I sort the array and traverse the array, if I have heavy duplicates, I end up repeatedly traversing the array in spots that I don't think it should do that, and I especially I iterate over elements I've already removed or already processed, like multiple times, which is kind of a problem from a performance perspective. Technically, I can make this like a set where I remove the elements that I'm putting into each subsequence, but that adds a lot of extra overhead. Adds logarithmic overhead, and also like just the processing itself is clunky. I was thinking maybe I could use a frequency map instead, and that might be easier, but actually it's not much better. You know what I could do? Might be better. I could use the frequency map, and then I would have 2 pointers. Okay, that's the better. Using a frequency map, I can use 2 pointers, and I can say remove the minimum of whatever elements I'm looking at here. And it's guaranteed to delete one of the elements from the array. And then I can have a pointer of like where I stopped, or where I should start. Where I should begin on the left side and where I should begin on the right side. I can maintain these two left and right pointers. That way I'm either always moving the left side over and bringing it back up to the right side, and they start at the same spot. Or I'm moving the right side over, and even though I start at this left spot, that's like where I pick the next element from. But where I begin for the element, or where I begin my subsequence from, is the left side, but where I check elements from is on the right side. And it's guaranteed that at each iteration, one of these 2 pointers is going to move at least one to the side. Yeah, that'll guarantee a linear time processing. That's a little bit confusing, but yeah, if I use a frequency map, I can guarantee that, and I can avoid a lot of extra overhead there. So we're going to use frequency, static frequency, and integers. And we're going to say instead fill, we're going to update it each time. Okay. Fill that with zeros. So we're going to use like a counting sort type of thing. Okay. We're going to have a left, right. Come back to this, I think. And okay. Something like this. So I'm going to say if frequency, so while frequency of L is less than or equal to 0, increment L, constant value equals frequency, or L. Then we're going to say current amount. It's going to be frequency of L. We're going to say while and L is less than 100,001. And then we say while right is less than that. And we're going to say helpless K is less than or equal to R. And we increment R. Say frequency of R is greater than 0. Then we're going to say, we're going to update the amount to std min of frequency of R, frequency of L, or amount. And we're going to this doesn't really work. No, that doesn't. This doesn't make sense. The problem with this one is that while one of these two get removed, the issue is that the entire sequence that I'm interested in could get smaller and smaller, and I'd have to decrement that whole subsection at once, which means I'm not actually going to be removing the left to right side one at a time. It's confusing. All right, I think I'll just use this set, keep it simple. Never mind. That doesn't quite work the way I thought it would. Doesn't quite work the way I was hoping it would. We're just going to keep it simple. Use a multi-set. Hopefully I can use a multi-set here. Excuse me. All right. So we're going to say second while loop. And it's going to go like this. Previous value. Bottom or left value. While that's not empty. Again, is not equal to previous. Oh, this is very tricky. If I remove the element, it invalidates the iterators. Oh my gosh. Okay. Okay. uh, target. All right, while else is not empty, and the target and left plus k is less than equal to the target. Then we're going to say auto pointer equals files.find target. I'm going to say target equals if files.size is greater than 1. Target is going to be equal to pointer plus 1. So while pointer is not equal to end, and pointer plus 1 is the values.end. Let's do pointer plus 1. Okay, here's the tricky part. So we're going to increment the pointer next pointer. I don't know about this one, man. I don't know about this one. Okay. Find the target. Now we're going to get the next pointer. While it's not equal to values end, and it's not equal, and it is equal to target, then we're going to update next pointer. Okay, there's something kind of subtle going on here, but that's what we're going to do. And we're going to delete pointer. Say vals.erase pointer. And we're going to say I actually think we can leave this value where it is. Okay. So basically we can keep doing this. Okay. Hmm. Um, this isn't quite right. I actually think it's this one. Should maybe explain what I'm thinking here. Trying to work through this. So let me try to explain this. Okay. So I'm going to try to use a set-based implementation, and I'm going to use a multi-set, and the idea which can contain duplicates. And the idea is that I count the subsequences directly. And the way this is going to work is I'm going to see if we still have elements in the set. We're going to set the previous value. We actually don't need this previous value. We could just use this left value, which is going to be initially the beginning element of the set. And the target is also going to start at the beginning. And I'm going to say, okay, as long as my left plus k is less than or equal to that target, then that target can be included in this subsequence. And so I'm going to find where that target is, because I'm going to be deleting elements from the set. So I want to use the find correctly here. Find the target, set a pointer there. Then I have this next pointer that starts at the same spot. And then I'm going to say, okay, now the reason why I'm doing it this way is that when I run into duplicates, I don't want to start at the beginning each time. I only start at the beginning at the start of this, but each iteration it may be it might jump around a bit. So I find this target, then I say, okay, give me my next pointer there. Now we're going to iterate this next pointer across all the duplicates. So that's what's happening here, is that if the... I could be doing this slightly wrong, because I think multi-sets actually have like buckets of elements that are the same, so this may not be quite the correct way to do this, but assuming that this is fine, this may not be fine, but I may have to double check it to come back to this. But what's going to happen is we're going to iterate across all the elements that are the same until we get to an element that's different. That's going to be the next pointer. And then if we found one, is what this check is looking for. We didn't find something different, meaning we went off the edge. If we went off the edge, we should erase the value, still do the erasure, but stop and break. But yeah, if we found something, they're going to erase the thing that we started with. on the left side. Now we've skipped over a bunch of the duplicates, and now we're going to set the target to be the new value that's not equal to the one of the duplicates. So this logic may be actually a little bit simpler using multisets, but I have to double check how the multisets are structured. But assuming this is basically just a set with duplicates, then this idea is, I think, reasonable. Now when I look up the next value using target, it's going to skip all those values that we skipped before. And then go through the same process again, find the next element to pick up and delete one of these. And it's going to keep doing that all the way across, so it'll kind of take a whole bunch of values as long as they're in this range of left plus k. Then if val is still not empty, starts again from the beginning and then just repeats the same process. And each time, this increments the count once. So each time this completes, we increment the count once. And that's it. I don't know if this is going to be correct. I could try it. So, what's up, Doom Gamer? Where do you work? How's it going? Welcome, welcome. I'll say in a moment. Give me a review of my account if you do, my handle. Sure. What's up, Real Sachin? Day's going well. Welcome, welcome. Sure. I suspect this code is like super custom, so I don't know if this is really going to work. But not custom, but it's super like unusual. This is probably not the best way to do this, by the way. Let me see. I think I can do like a user account type of thing. Yeah, there we go. 5 a chin. Okay. Page not found. Let's see. So, oh, it's pretty good. You've done some competitions. I haven't done any of the competitions. I don't want to do the competitions until I've solved all the problems at least once. So I haven't done any competitions. Punjab, India, global ranking. Global rank's pretty high. It's relatively high. 35k out of 875k, 74k. Yeah, top 4. Oh, where's this? You're around here. It's pretty high. It's good. Solved a bunch, which is good. Solving 100 hard is good. The hard ones are really the ones that are tough. These, in my opinion, these are the ones that really are really challenging. I mean, I like to do the easies and mediums because I like to kind of like look for micro optimizations and things like that. But the hards are very tough overall. They require a lot of like creativity. You know what actually really it is? The hard ones, I would say it's more knowledge based. You gotta like learn like tough ways, not tough ways, but you've got to learn non-obvious solutions. And it's not really realistic to come up with them on your own. It's much more realistic to learn them and then have them available when you solve problems. That's good. I like that you've solved 100 hards. I think this is probably one of the stronger indicators is how many hard problems someone solved. It's good to solve easies and mediums, but the hard ones are really quite a bit more challenging. It's good, man. C++ is good. I like C++. It's definitely more, I don't know what the standards are now for, you definitely want to have a higher acceptance rate though. You mostly, when you solve a problem, you kind of want to like be sure it's the right answer. Your acceptance rate, you typically want it to have around like 90%. Mine is a little bit lower because I tend to get like frustrated and just submit things. But yeah, it's a pretty good rank overall. What else can I say here? Yeah, it's good, man. It's good. How many? Oh, it's only a couple of years. Wow. So you've been just grinding, huh? Um, Last year and this year looks like. That's pretty good. That's a lot of work, dude. um, what else is there to say? It's good, man. Just keep up the hard work, I guess. I don't know how much you need to solve for like FANG companies. I keep hearing you only need about 150 problems overall, but that's also like a few years back now. I think the standards are really high now. I don't really know how hard the questions are at the FANG companies now, but yeah, LeetCode is more FANG style stuff. If you're interested in C++, you might want to look at if you want to do HFTs or you want to do what's the other one? The fintech HFTs, these sorts of things. They use C++ extensively, and if you're interested in that, you can go for I'd say like Top Coder, like other platforms that are more competitive programming focused. LeetCode is competitive programming, but it's not as difficult, and it's more around interview questions, which are different than competitive programming questions. They're easier, but they're more focused on other elements, other aspects. Whereas competitive programming is much more like raw speed, raw knowledge, that kind of stuff. And they kind of expect you. It's a very clear format of like they want you to do competitive programming, learn the algorithms, that sort of thing. Whereas LeetCode it's a similar sort of a way to approach it, but it's also it's a different style. Like I said, it's a little bit easier. It's more about like interviewing than it is about like just getting the raw answer. Um, so yeah, but yeah, C++ tends to be more fintech HFT. That tends to be more on the competitive programming side. They tend to look for like highly ranked, like Top Coder and other sort of sites like that are more focused on competitive programming. So there you go. There's some feedback for you. Hopefully that's good. Um, but yeah, okay. So how did we do here? Iterator. Oh, whoops. Oh, whoops. You could tell I'm kind of struggling with this question. There's so many elements to it that I'm like not so familiar with. I'm not able to like fly through it. TLE. Oof. Oof. Oh. Oh boy. Okay. Interesting. Uh. Huh. Hmm. What happened? But yeah, like I put this here in my code, but they in interviews they're not really going to care if you have that in there or not. Um, Competitive programming stuff they care about that, but not. Okay, so it just stays at 5. Huh? Competitive programming stuff will not look for this, but they'll use this kind of thing. But basic interviews are not really going to care about that. Okay, so it is. It is. So something's not getting deleted here is the issue. And I don't know if I think there's a way to check if the pointer was erased or not. Um, I don't remember. Check if stood set succeeded. So, yeah. Not quite sure what to make of this. Oh, I know what's wrong. That's a mistake on my part. Oh, yeah, okay. This has to be greater than or equal to target. Yeah, left plus K has to exceed the target. That's my mistake. Oops. That was a logical thing on my part. I was like, what am I doing wrong here? Now, there might be an issue with the multi-set that I'm using that might make things a little bit more confusing. Oh yeah, where do I work? I currently work in fast food. I also am looking to start my own company at some point, be a bit more entrepreneurial. I think I got 4, should have been 3. Okay. Wait, what? How is this 3? Maybe I misunderstand how this works. But yeah, I'm looking to do something a little more entrepreneurial because software developer employers can be pretty cruel at times. Okay, hold on. What about example 3? Explain this. 3 subsequences. Oh, wait. Each element appears in exactly one of the subsequences. Oh no! Oh, I must be getting tired. Oh no. Ah, I goofed, man. I goofed. For some reason, I thought the subsequences had to have distinct elements. That's why I was doing so much of this extra stuff. No, I didn't realize it's a partition. Oh, shucks. Oh man, I did that wrong. Oh, okay, yeah, you could use it. You could just use a sliding window. Oh my gosh. That's a mistake on my part. This is just a sliding window. Jeez, man. Okay. Sort it in sliding window. It should be fine. I don't know if there's a faster way to do this. There might be. Actually, yeah, let's do the counting sort version is actually faster. I goofed, man. I goofed. Okay. Whoops. Oh man, I should have solved this so much faster. That's funny. Whoops. Yeah, so we can do 4 left 0, right is 0. Um I actually think a double loop is fine. Well, okay. Right is less than. I'm gonna try to do it this way. Okay. So we're gonna say while L is less than 1,000. Frequency of L is 0. Increment L at R. Okay. What we're going to do is shift R. So while we don't need this too. So using for loops. While the right side is less than 1,001, and the right side is less than L plus K, less than or equal to L plus K. We're going to increment R. We'll check equals true. Just say check or equals frequency of R is greater than 0. I think that's all I gotta do, something like this. It's a bit involved, but it's something along these lines. This. What's up, Ion? Welcome, welcome, howdy, howdy. That's kind of cool. I like that symbol. Hi. Oh. Hover over, it gives me a hi. Interesting. TLD. Okay. And then we're just gonna set L equal to R, I think. Something like that. What did I do now? And then we just do another. It's confusing. I have to like think this through a little bit more. This is maybe not the best way to do it. Maybe I should just use a double loop. Keep it simple. TLE. It's getting stuck somewhere here. Let me just do a double loop. It's probably easier. Let's just do it that way. So int I0 is less than 1,001. I int J0, she starts at I. And we're going to increment the count. We just say while it's less than 1,001 and frequency of I is equals increment I. Then we keep incrementing J, and then we have a Boolean check equals false. If the check is going to be or equals frequency of J is greater than 0. So if at any point we find an element, it's not going to be an empty subsequence. And we say, well, I plus K is greater than J. We're going to keep incrementing J. And then at the end of this, we're going to set, we're also going to increment I think. Oh no, we're not. Yeah, and then we just say I plus equals k, I think. Yeah, something like this. Definitely have some weird things going on here. Let's try this one. This one I think is a little bit better. The other one was pretty confusing. Wrong. Okay. Output 0 expected. These ones are correct though. 2, 4, 5. Oh, yeah, I think k is 0. That's a little bit confusing. Oh, I think we do greater than or equal. And then, I mean, you could just do std min or std max 1 k. I mean, you could do that too. So it always increments at least 1. No. Doesn't quite work for k is 0. Guess I could handle that separately. Which case? I think something like this. Might be easier to just handle that separately. Let's try a bunch of other test cases. That's too big. Okay, let's go with something like this. And let's also change the values of k for each of these. This like 10, this like 100, even 1,000. Okay, it looks correct. I'm gonna go for it, I think. Yeah, I mean, it's pretty wonky, quite frankly. It's a good chance it's a mistake. Oh, that's right. Okay. Yeah. Okay. So yeah, it's on the faster side. It's pretty good. It's pretty awkward, to be quite honest with you. It works, but it's maybe not the best. Let me try this again. Also, let me see how much time we have. What's the stream doing here? It'll end up being more like 3 hours. All right, not ideal, but not the worst. So yeah, it's definitely, it's on the faster side as far as solutions go, but it's not the fastest. Let me try again. Yeah, beats most solutions, but it's not the best. Yeah, sliding window is definitely the way to go. Sorting, it's fine, but using counting sorts a little bit more efficient. Oh, I should probably do this actually. This is actually a slightly more efficient way to do it. Oh no, but I do still need, never mind. I was gonna say I do still need the frequency map sorting. Yeah, I mean, to get the absolute highest speed, I probably would need to be able to do something a little more clever. I get so excited when I see them 0 milliseconds. Yeah. I like using for loops, man, instead of while loops. For loop would be like this. I mean, the problem with this approach is that it does use sorting, even if it's sort of a linear sorting. It does use a lot of sort of a lot of extra memory, I guess. I could use a regular sort for this and try to do a similar thing. But yeah, it's a sliding window kind of a solution. It's not too bad. It's not too bad. All right, that's probably enough for now. It's okay. It's not the best. Let me plug it into. Oh, I can by examining the return value. Okay. Returns 1 or 0. Interesting. Does not a return. Returns an iterator. Oh, that's good. Okay. Doesn't return a failure code. Okay. Huh. All right. Let's do this. Yeah, I don't seem to be getting the 100% there. Sliding window that you've used? I don't know much about counting sort law. Yeah, it is sliding window. It is sliding window. So counting sort's not too bad. Basically, what I did was so the basic algorithm goes like this: sort the elements, take a left side and a right side for your sliding window, and you're gonna start on your left side and say, okay, what's that element? Let's say it's 5. Then move right to left on your right side of your, so like L and R you could use. So move R over to the right for your sliding window and keep picking up elements that are, I think it's the minimum and the maximum. The difference has to be at most K. So that means that L plus K, any element that's less than or equal to L plus K. So as long as R is less than or equal to L plus K, which L plus K is like somewhere over here, as long as R is smaller, you're going to keep moving across. So you move R over. Then you stop at some point, somewhere around L plus K, and you say, okay, add 1 to the number of sequences that we've processed. So that one's going to be 1 sequence. Then move L over to where you stopped where R was, and then repeat and move R over again. And you just kind of keep going section by section like that. So it's a form of sliding window. It's now what I did, which was a little bit more sophisticated, slightly more sophisticated. Instead of just sorting it first, I used counting sort, which means I basically counted the frequency of each element first, and then I used a frequency map, and then I worked through the frequency map. Frequency map basically just means like at index 0, you have the number of zeros. At index 1, you have the number of ones. At index 2, number of twos, etc. It's like a very simple kind of way of counting the number of times you see an element in a sequence. And the reason I was able to do that is because the bounds, the constraints on the inputs, this largest element you're going to see is going to be 100,000, which is also the number of elements, the largest number of elements, and k is also bounded by 100,000. So everything is bounded by 100,000, which means that like even if I walked through the whole list, which you're going to have to anyway, no matter what algorithm you use, it's going to be you have to go through the whole list. You're still going to do 100,000 operations. So just having a memory block of 100,000 and then just assigning each element to its own index and incrementing that index in the frequency map that allows you to just count how many elements of each type you've seen or each number you've seen. And why that's more efficient is that sorting usually has an n log n time, meaning there's an extra logarithmic factor involved, whereas if you do counting sort, you only have to go through the list once, which is linear. It doesn't have a logarithmic factor, a multiplicative logarithmic factor, and you can just count how many times you see each element. And then what it does is it's naturally sorted. So now you have at 0, you have a certain number of zeros, and then at 1 you have a certain number of ones. And if you go left to right through those indices, that's already in order. And so you would just count, you would just take the number of each frequency. So like if you wanted to actually generate this sorted list at that point, you would just say, okay, give me the number of zeros, put that in this section, give me the number of ones, put that at the next section, number of twos, next section. And then if you have 0 things, you just don't put anything there. You just skip it. So it's very efficient. So that's why I figured it'd be a little bit more efficient if I statically define the memory and then I just wipe it with a simple instruction at each call. Yeah, and the sliding window part that I described, like I basically just use this value of j and I shift it over a bunch. And I'm just basically looking to see if any of the elements in between are exist, like if it's not empty, and then that allows me to count that section, and then I can just shift over I. Yeah. There may actually be an even faster way to do this, quite frankly. But this is reasonable. This is okay. Yeah, actually, I don't really even need counting sort, quite frankly. Not really. I don't know. This probably would optimize this. Got it. Yeah, hopefully that makes sense. Yeah, hopefully that makes sense. That was counting sort and then like how I used it. Okay, while creative has logical flaws and is less efficient than standard greedy sorting solution. Okay, incorrect logic for grouping, inner loop, range values at the end, potential skips potential groups incorrectly. Sure. Sometimes it like thinks you had a logical error, but it just kind of didn't understand the code fully. Values indices 13, 10, and 13. Starts at 10, checks out 12, finds 10, sets check equal 2, increments count, I becomes. Starts at 12, skips 13, also happens. No, there's no loop increment. Oh, there is. Did I use a loop increment? Oh, I did have a loop increment there. Oh. Oh, whoops. Whoops. It's a good thing I checked this. Oh, I may have made a mistake there, huh? Nope. No, that's supposed to be there. That's subtle. Yeah. Hold on. So that was incorrect. O of M, regardless of input size, and is small, slower. O of M. Okay. So uses extra memory. Redundant. General logic should handle k equals 0 naturally. Each distinct number forms a group. Special case against code cloud performance gain. No, no, I don't think it's handled correctly. Maybe I'm wrong. Maybe it is handled correctly. I don't realize it. Oh, it is. Okay, never mind. Oh, wait. Okay, never mind. I got confused. Interesting. Although I think it's more efficient to use to handle this case separately. Maybe not. I don't know. Okay. Oh my gosh, man. Sometimes the AI is getting a lot better. It really is. So 134k equals 2. 134k equals 2. Okay, hold on. I don't think so. I think this is fine. Nope. It's correct for the specific subset. Passing is all that matters. Interviews, sorting approach is preferred. It's logically simpler to prove it's correct for all cases. Okay. By the way, yeah, I don't know why. I don't think it has any logical errors here. think the code is logic sound. I think I also put something in here that'll increment I anyway, potentially, yeah. Mm-hmm. Oh, I don't really need that inner loop actually. This check is already true. Inner loop is completely unnecessary. Oh, whoops. Oh, it's wrong. Oh no. Hmm. Uh, oh. Huh. It's just an off by one or something. Um, oh, there is something subtle here. There is something subtle here. Still wrong. Shoot. No, this is wrong. Um, there we go. A bit subtle. Oh, brutal. Brutal. It's not correct. Okay. Oof. That's a rough one, man. Oh no. So there's something subtle here. Excuse me, I don't know why. I did something wrong. Okay, I got one, it should be two. Okay. Oh, that's fine. That's also very subtle. That's also very subtle. Very slight logical issue there. There you go. Okay. Yeah, ouch. Ouch. Got a wrong answer there. There we go. So this is definitely a little bit cleaner than the other one. Let's try this again. So yeah, it's not huh. So this is a little bit more efficient. Yeah, we only care about existence. So yeah, I can optimize a little bit here. So we can use bools. And we can also use um, I think it's actually easier to do with the presence of or frequency of present exists. Yeah, that's a lot cleaner. Um, yeah. I like that better. TLE, what happened? Oh, I'm gonna go for it here. So it's only supposed to be 2 hours, but it ended up being it's not much more efficient for whatever reason. Still on the slower side. Hmm. Hmm. Cleanest and most optimal version. Hmm. often faster than sorting when it's large. The range of m is fixed and manageable. I'm wondering if the standard sort is faster for this test suite. Yeah, I keep getting on the slower side. Oh, I have an idea. Hello, where are you from? What's up? Himan Chatawat. What's up, man? Welcome. Hello. Give me 1 second. Oh. Hold on just a moment here. I am from the USA. The USA. Howdy. Welcome. Hmm. I'm gonna go for it here. See how this goes. Oh my goodness. No. That's funny. Why is this wrong? What? I think this needs a +1. That might be why. That might be the issue. That's subtle. That might be the problem. Got a bunch of wrong answers here, man. These very subtle, slight changes and differences. It's off by 1 errors. All right, so this one, it's not much better though. I think it's not better. Critical bug. Is there any bug? No. Hmm. I think you're right. That's good. I think they're right. I think that's actually faster. I think it's cleaner. Okay. I did get the off by 1 error, by the way. Yeah. Oh, still not the fastest. All right, let's look at the fastest solution. So my solution was fast, but it wasn't the fastest. So what did they do? We'll look at it in a moment. It's really fast. It's not the fastest. It's starting to get kind of stuck. Yeah, the AI systems have various like limitations. This one definitely is getting better though, for sure. Oops. It might start slowing down a bit. Oh, maybe I can optimize a little bit further here. Are you ready for this? I don't know. Hopefully it's correct. Okay. It's fast, still not the fastest. Likely the fastest possible. Okay. Oh, there you go, 100%. Yes. Right. What does this say? Minimizing overhead and adapting input size dynamically. Your code hits the sweet spot where algorithmic efficiency meets low-level hardware optimization. Cache locality and branch prediction is a great example of how tweaking the implementation details can squeeze out every last millisecond of performance. Okay. Let's see if this is still correct. Ooh. I might need to start a new window here. Yeah, we got the 100%. It's pretty good. It's pretty good. I think it's actually slower adding the min value. I could be wrong. Cool. That's quite good. There we go. The fastest possible solution. There you go. There you go. That's how it's done, man. That's how it's done. All right, that's a good spot to end here, I think. 3.5 hours is kind of a lot. So thank you all for watching. I do appreciate it. I think I'm gonna get going here. But yeah, definitely interesting so far. Great, man. I like that. That's cool. Very cool. Yeah, I think we'll just stop here. I don't know what else to do or to say. I guess I just go on and leave. So thanks again for watching. Have a good rest of your day. If you like the stream, don't forget to like it, subscribe, all that stuff. Recommend it to your friends. And yeah, all right, take care. I'll stop here. But yeah, that was cool, man. Ending on a 100%, definitely positive. I was wondering why my code wasn't as fast as it could be. That's a pretty good solution overall. That's a pretty good one.